let's start off with the history of quantum mechanics. So, physics, the principles of physics um, that were established before the end of the 19th century, that would be what? Late 1800s, okay, early 1900s, are now called what we call, it's now called classical physics, okay? And at that time, around that time, there were several anomalous experiments that led to the development of what we now call modern physics. Okay, so the physics that they knew at the time is now referred to as classical physics. And basically, what that meant was what they thought was right turns out not quite right because of these anomalous experiments. So what are these anomalous experiments? We're going to go over them in this chapter, okay? But um, the failure of classical physics to explain these phenomena led to the development of modern physics, and those are the two main branches would be relativity and quantum mechanics. So basically, at that time, they found things that could not be explained by the physics they knew at the time, and so it failed to explain things that were happening in the world of the very fast, things approaching speed of light, and so that led to the development of relativity. It failed to explain things that were happening in the world of the very small, like atoms and electrons, and so that led to the development of quantum mechanics, okay? The other branch of modern physics. And most of these experiments that led to the development of quantum mechanics had to do with light. Okay, so we're going to talk about light. And light, as you know, is also known as electromagnetic radiation. So what's an electromagnetic radiation? Uh, Electromagnetic has to do with the fact that it's associated with charged particles. Okay, so behavior of light can be explained as, from Maxwell's work, as an electromagnetic wave. Okay, so the idea is this: if you have a wave is a periodic disturbance that propagates through space. Okay, so it's a repeating disturbance. That's what periodic means. Okay, and electromagnetic, that adjective just tells you that it's got something to do with charged particles. Light is produced by oscillating charged particles. Okay, and a wave is like I said, it's a disturbance. It's basically a way for energy to transfer from one point in space to another. Okay, so like imagine you were to drop a rock on a pond. What happens? You got ripples of water emanating from where the rock fell, right? So you have a wave. What would happen if you have something like a cork somewhere away, a few meters away from the rock, from where the rock fell? Once the wave passes it, what happens to the cork? It ends up bobbing up and down. So you've transmitted the energy of the rock to the cork. So the wave is the mechanism by which energy is transferred from one point in space to another. Okay? So exactly what is it that's waving in an electromagnetic wave? It would be electric and magnetic fields. And just to review your physics, an electric field that's the Coulombic or electrostatic force that a charge of 1 coulomb would feel at a given location. So the electric field the unit for it is newtons per coulomb. Okay? And it's strongest at the crest of the troughs. Okay, so a wave like this you can represent it by a sine wave like this. Okay, and at the crest, this right here, the magnitude of the electric field is strong, most positive. That means a charged particle at that location would feel the strongest force directed upward if it's positively charged. And at the trough right here, at this particular location, the force that a charged particle would feel would be downward, right? That would be strongest. So that's a trough. This is the crest right here. And where the locations where the particle doesn't feel, a charged particle would not feel a force would be what we would call a node, right? Now, the magnitude of the electric field at the troughs or the crest, this magnitude right here, okay, this value of the electric field at the crests and the troughs, the magnitude of that is called the amplitude of the wave. Okay? Now, the magnetic field wave is perpendicular to the electric field wave. So if this was like the xy plane, let's call this the xz plane. Okay. So if this is the z-axis and this is the x-axis, okay, your magnetic field is going to be oscillating like so. Okay, it would be on the xy plane. Okay. Let me show you an animation that shows that better. Let me see. Animation, electromagnetic wave, right here. See, you got an electric field, okay, and then perpendicular to that, you have a magnetic field, okay. So let's do a quick check here. Here's a snapshot of the electric field component of an electromagnetic wave as it travels through space. At which of the locations indicated here would a charged particle experience the strongest force? At point A, B, C, or D? A, because strongest force in which direction? In the downward direction, right? That's if you have a positively charged particle. Of course, if you have a negatively charged particle, the force would be the other way. Okay? And B and C are right around the node, and D is not quite at the crest and not quite at the node. Okay. All right. So the speed at which the wave travels, electromagnetic wave travels, is 2.998 times 10 to the 8 meters per second. That's given the symbol c. That's the speed of light. Okay. The distance between consecutive crests is, so for each cycle of the disturbance, each repeating cycle, the distance that is the wave travels is called the wavelength. So the crest-to-crest distance or the trough-to-trough distance is lambda. The Greek letter lambda is used to represent wavelength. Okay, the time it takes for the wave to travel at distance lambda is called the period of the wave. So the frequency is the number of cycles that would pass through a given point per second. It's just 1 over the period. Okay, so the speed is the distance traveled divided by the time it takes to travel that distance, and 1 over t is frequency. Frequency is represented by the Greek letter nu. So lambda over t would just be lambda times nu. Okay, so that is the speed of light. So lambda nu is equal to c. Right. So that's in vacuum. So what's the frequency of electromagnetic wave that has a wavelength of 250 nanometers? How would you solve for this? C is lambda nu. So nu is equal to c over lambda. What's the speed of light? 2.998 times 10 to the 8 meters per second. By the way, the speed of light is an exact number. It's defined to be an exact number now. Okay, and it's this definition of the speed of light and the definition of how long a second is that's used to define how long a meter is. Okay. In fact, what's the exact value of the speed of light? Here, 2.99792458 meters per second. That's an exact number. Okay. So when you round that off, make sure you don't round it off too much. You want, let's say, if you have a calculation where your least precise term has only 3 sig figs, then you have to round it up as 2.998. Okay, but if you have more sig figs than that, then you're going to need more sig figs for your calculation for speed of light. Okay. So 2.998 times 10 to the 8 divided by 250 nanometers. That would be 250. What's a nanometer? Nano is 10 to the negative 9. So 250 times 10 to the negative 9 meters. So meters cancel out. Oops, what did I just do? So that gives you how much? 10 to the 8 divided by 250 times 10 to the negative 9 exponential notation 1.199, so 2 sig figs 1.2 times 10 to the 15. Okay, so this is 1.2 times 10 to the 15, and the unit is per second or hertz. That's the frequency. Okay. So what's the answer? B. What time is it? Amplitude, is related to the intensity of the radiation. Okay, so what we associate with the intensity of the radiation, or in layman's terms, the brightness of the light, would be is related to the square of the amplitude. Okay, so the square of the amplitude multiplied by speed of light c multiplied by epsilon naught, the permittivity of vacuum, which is this value right here, 8.854 times 10 to the negative 12 coulomb squared per Newton per square meter, okay, times 1/2. That gives you the intensity. The intensity of light is defined as the energy that's delivered per unit time per unit area. So what's the unit for intensity? It's energy per unit time per unit area, joule per second per square meter. Okay, so joule per second per square meter, and a joule per second is just a watt, so that's a watt per square meter. That's the intensity of your radiation. Okay, so if you let's do a calculation right here. Let's say you have a 5 milliwatt laser beam that has a cross-sectional area of 2 square millimeters. What's the intensity of the beam? What's intensity? Energy per unit time, right? Per unit area, right? So 5 milliwatt is millijoule per second. So that's energy per time, right? By the way, what's energy per unit time called? Power. Okay, so it's power per unit area. So this is 5.0 times 10 to the negative 3 watts. Okay, let's call that joules per second. A watt is a joule per second. Milli means 10 to the negative third. So that's a quick way to do your conversion. Okay. Nice to know all of these SI prefixes. Divided by the area, which is 2.0 square millimeters. What's a square? What's a millimeter? So 10 to the negative 3 meter. And so you just square that. So you got all your units converted right away to the base SI units right there. Okay. This is intensity S, right? So what's 5 times 10 to the negative 3 divided by 2 times 10 to the negative 3 squared? So you have 5 times 10 to the negative third divided by 2 divided by, this should be 10 to the negative 6, right? So divided 1 times 10 to the negative 6 equals 2,500. Is that what you're getting? 2.5 times 10 to the third. No. You are not using this formula actually, because you are already given how much power, how much energy you're delivering per unit time. Now you can use that to calculate. That's actually a follow-up question to that. Calculate the amplitude of the radiation. So this is 2.5 times 10 to the third joule per second per square meter. Okay, so now let's use that now to calculate the amplitude. out B. So what's the amplitude in this case? We're going to say now that the amplitude is, how do we solve for the amplitude here? Amplitude is equal to 2s over epsilon naught c, and then you take the square root, right? So let's calculate that. Square root of 2 times 2.5 times 10 to the negative 3 joules per second per square meter divided by epsilon naught is 8.854 times 10 to the negative 12 coulomb squared per Newton per square meter times speed of light is 2.998 times 10 to the 8 meters per second. What would that be? Bring up MathCAD here. I like to use MathCAD. We're going to talk about MathCAD in the lab, so you'll know how to use this program. Okay, so what do I have here? Square root of 2 times 2.5 times 10 to the negative third joules per second per square meter divided by 8.854 times 10 to the negative 2 times negative 12. Okay. Times newtons, coulomb squared times newtons, negative 1 meters to the negative 2 times 2.998 times 10 to the 8 meters per second equals 1.372. This should be newtons per coulomb. 1.372 newtons per coulomb. Okay? Is that what you're getting? 1.372 or 1.4 newtons per coulomb. So that would be the amplitude. Did I take the square root of that? Yeah, I did. All right. How do we interpret wavelength? Wavelength is related to what we perceive as the color of the light. As you know, visible radiation ranges from 400 to 800 nanometers. And the term electromagnetic spectrum refers to the range of possible wavelengths. And so it goes from very short frequency to very high frequency. So the type of electromagnetic radiation that your eyes are sensitive to, the ones that your eyes can detect, perceives as color, only refers to those with wavelengths ranging from 400 to 800 nanometers. So near the red end of your electromagnetic radiation, you have the 800 nanometers around here, and near the violet end, you have 400 nanometers. Okay, so past the red, you have longer wavelengths. Those types of electromagnetic waves are called infrared, and even longer wavelengths you have microwaves. Okay, and then longer than that, you have radio waves. So what type of electromagnetic radiation is 102.5 megahertz? That's your FM radio station, right? So that's a radio wave. Okay. And the radiation in your microwave oven will be longer than so it's past the red end of your electromagnetic spectrum. So the terms red and blue are usually used as adjectives when referring to things related to waves and light. You say there's a red shift, that means shifting towards longer wavelengths. A blue shift would be shifting towards shorter wavelengths. Okay, shorter than violet would be ultraviolet, and then even shorter than that would be X-rays. So, so that's going to longer wavelength, and that's a longer wavelength means lower frequency. Why is that? C is lambda times nu, right? So if nu can be written as what? C over lambda. So you can say that nu and lambda are inversely proportional. So the longer your wavelength, that means the lower the frequency. So radio waves would be what you would call low frequency radiation. All right, let's see. What type of color corresponds to longer wavelength, red or blue? Red. What type of radiation corresponds to the longer wavelength, microwave or X-rays? Microwaves. Now, what evidence do we have that light is a wave? One experimental evidence for light being a wave is diffraction. Diffraction refers to bending of waves when they pass through a barrier. So, like if you were to pass light through a slit, a very narrow slit, okay, you'll find this pattern right here. This is a single slit diffraction pattern. So right here you have a very high intensity in the right where the slit is around. So if you were to have a screen back here, your light's going to be very bright over here, right? Now, normally you would expect, okay, if you were just have to throw, let's say you have that hole right there, you were just going to throw sand across that, okay? You would expect it would be, that the distribution would be something like this, right? It would be, most of the sand is going to hit right around here, and then it's going to taper off to the sides, right? So you do see that tapering off, but you'll notice that there's this pattern right here, okay? That's called a diffraction pattern, and that's, so it just doesn't taper off monotonically, all right? So it goes to 0, and then it goes back up a little bit, and then it goes back down to 0, and so on. So that's called a diffraction pattern. So you see these dark spots right here, and then it becomes bright again, and then it gets dark again. Okay, that can only be explained by thinking of light as a wave. Okay, so that's evidence for wave behavior, and the way you interpret that is when you get to these dark spots right here, those are spots where when the wave hits that spot, you have what's called destructive interference. So if you have a wave emanating from here and another wave coming off from here, and when they hit this point right here, if they destructively interfere, then you hit a dark spot. Okay? And so that's how you explain diffraction. And when you get these very bright spots, that's where you have what's called constructive interference. Okay? So that's how you explain diffraction. Now, the notion of light as a wave is referred to as the wave model of electromagnetic radiation. But towards the end of the 19th century, there were several experimental phenomena that led to the notion that could not be explained by thinking of light as a wave. Okay? And so these phenomena generally dealt with interaction of light with atoms and molecules. So when you have light interacting with you have light interacting with small particles like atoms and molecules, the behavior of the light could not be explained by thinking of it as a wave. And the solution to that anomaly was to think of light as though it's a stream of particles, behaving like it's colliding with the atom, or it's like as if it's a particle that's colliding with the atom or the molecule or the electron. Okay, so we now say that light has a wave, as a dual nature. In some instances, you can explain its behavior by thinking of it as a wave. In some instances, it's best to think of it as a stream of particles. We now refer to these particles as photons. So we say light has a dual nature. So this phenomenon is known as wave-particle duality. So the term wave-particle duality refers to the fact that light, which we traditionally thought of as a wave, sometimes behave as though it's a stream of particles. Okay? So the energy of each of these photons, each of these particles, turns out, based on these experiments, you can resolve all of these anomalies by thinking of each photon as carrying an energy equal to h times nu, where nu is the frequency of the light. So there's a connection between the wave nature of the light and the particle nature of the light. So light that has a frequency nu we say is made up of photons, and each of those photons carries an energy equal to h nu. Now this h right here, this proportionality constant, is called Planck's constant, in honor of Max Planck, who was the first to propose the idea when he dealt with the black body radiation, which we're going to talk about next time. Okay, so Planck's constant is 6.63 times 10 to the negative 34 joules second. Okay, 6.626 if you have 4 sig figs here, times 10 to the negative 34 joules times second. Basically, what this equation says is the higher the frequency of the radiation, the more energetic the photon. Okay, what's the unit for the energy of the photon? The unit for h is joules per second. The unit for frequency is per second. So seconds and per second cancel out. That would give you the energy in joules. Okay, so you get more energetic photons when your frequency of your radiation is higher. So, simple example here. What's the energy of a photon of red light if that particular light has a wavelength of 632 nanometers? How will we solve for that? E is h nu. So h is how much? 6.626 times 10 to the negative 34 joules times seconds. And wavelength frequency is, how is frequency related to wavelength? This is wavelength. Lambda times nu is c, so nu is c over lambda. So this is also equal to hc over lambda, right? So what's the value of speed of light? .998 times 10 to the 8 meters per second divided by lambda, which is 632 nanometers. Nano is 10 to the negative 9 meters. Okay, so seconds cancel out, meters cancel out, so that gives you joules. What is that number? You have 6.626 times 10 to the negative 34 joule seconds times 2.998 times 10 to the 8 meters per second divided by 632 times 10 to the negative 9 meters. Oops, 0. Okay, let me change this sensitivity of the zero tolerance for this. 3.14 times 10 to the negative 19 joules. Okay? So that's 3.14 times 10 to the negative 19 joules. By the way, Just in case you're wondering how you work out those units over here. Let's go back to this one. This is joule per second per square meter over coulomb squared per Newton per meter squared meters per second. And then take the square root. Okay? Let's make this your first homework. Show me how this ends up being newtons per coulomb. Okay? Show how these units, joules per second per square meter over coulombs per Newton per square meters times meters per second. How all of those units, if you take the square root, ends up being newtons per coulomb. Okay. What are some of the things you need to know? What is a joule? A joule is a Newton times a meter, right? What's a Newton? Unit of force, right? So mass times acceleration. So a Newton is a kilogram meters per second. Mass times acceleration, yeah, per second squared. Well, at least you all should already know this part right here, right? Coulomb squared, if you take the square, it just gives you coulombs. So all the rest of this should give you Newton squared, and you take the square root, that will give you Newton, right? So let's make that your first assignment. All right. Which of the following regions of the electromagnetic spectrum has the most energetic photons? Which one? Most energetic photons. Highest energy, h nu or hc over lambda. Highest energy would be the highest frequency or the shortest wavelength. It would be X-rays. Which of the following characteristics of electromagnetic radiation is not associated with what we perceive as color? Wavelength, frequency, wave speed, photon energy. Which one? You know wavelength is related to color, right? So, because longer wavelength, lower frequency, lower photon energy. But speed is a constant. Typical photon energies are small. If you recall, what number did we get earlier? 1.4 times 10 to the negative 19 joules, right? So it's not a convenient unit to use for photon energies. Joules is not anyway. Very small if you do it in joules. So an electron volt is a more popularly used unit for photon energies. And a newer SI-based unit that seems to be getting some popularity is the attojoule, which is 10 to the negative 19 joules. Okay. 1 electron volt is the energy that an electron gains if you accelerate it through a potential of 1 volt. Okay. So a charge of an electron is 1.602 times 10 to the negative 19 coulombs. So if you accelerate an electron through a potential difference of 1 volt, that gives you 1.602 times 10 to the negative 19 coulomb volt. And a coulomb volt is just a joule. Okay, so 1 electron volt is 1.6 times 10 to the negative 19 joules. So that's a more convenient unit to use. So let's say you have a photon energy of 3.14 times 10 to the negative 19 joules. What would this be in electron volts? 3.14 times 10 to the negative 19 joules times 1 electron volt is how much? 602 times 10 to the negative 19 joules. Answer? .14 times 10 to the negative 19 divided by 1.602 times 10 to the negative 19 Oops. Entered the wrong number, huh? 1.6602 times 10 to the negative 19. Okay, that's clear. 10 to the negative 19 is just going to cancel out, right? So let's make that easier. So it's just going to be beep. Clear. Okay, so 3.14 divided by 1.602. Huh? 3.14 divided by 1.602 is just 1.96. So you can see, that's nice numbers to deal with, you know, easy numbers to deal with. What would be in attojoules? 3.14 times 10 to the negative 19 joules. What's an attojoule? 15. So that's just going to give you 31.4 attojoules. Okay. What's the energy of a photon of UV radiation with a wavelength up to 50 nanometers? We've done this problem already, right? Let's make that your homework. Okay? Uh-huh. Listen. And then this one, another homework. Frequency of radiation using a microwave oven is 2.45 gigahertz. So if you have a 600-watt oven, you operate it for 60 seconds. How many photons are you generating? I give you the answer. You should show me the word. Okay? So wave number is defined as 1 over lambda. And the typical unit that we use for wave number is reciprocal centimeter. So it's centimeters to the negative 1. And the way you read that, you say reciprocal centimeters. And so if your photon energy is equal to h nu, okay, and if you recall, h nu is c over lambda, right? Then you can say that your photon energy is hc times 1 over lambda. So 1 over lambda is your wave number. Now, usually this is represented by the symbol nu with a tilde on top. Okay, so this thing right here, that the wiggly line on top of the symbol for nu is a tilde. On your keyboard, that would be, that's the key to the left of the number 1 at the top of your keyboard, but you have to press the shift key. Okay, so nu tilde, that's what you would call a symbol, is a symbol for wave number. So that's 1 over lambda. And so your photon energy then would just be equal to hc times nu tilde. Just make sure though when you plug in your numbers that you do have consistent units. Okay? So reciprocal centimeter is commonly used, in fact, by spectroscopists as a unit for energy. Why is that? Well, the energy of the photon, you can see, is equal to some constant times the wave number. So it's proportional, directly proportional to the energy. So since in spectroscopy we're primarily dealing with light, energy of light, since wave numbers directly proportional to energy, it's used as a unit of energy. In fact, we can use frequency as a unit of energy. But reciprocal centimeters is such a very nice number. Those numbers, the reciprocal centimeter values we deal with when dealing with light typically tend to be nice, easy numbers to deal with. Okay, as you can see in just a short while, that it's commonly used as a unit for energy. Okay, so how many joules would actually correspond to one wave number? So the energy for a photon that has a wave number of 1 would be what? H is how much? Okay, 6.626 times 10 to the negative 34 joules second. Speed of light is 2.998 times 10 to the 8 meters per second. And 1 reciprocal centimeter would be 1. And reciprocal centimeter, we have to put it in meters. What's a meter? I'm going to put 10 to the negative 2 meters, right? Centimeter means 10 to the negative 2 meters. So 10 to the negative 2 meters, but I have to take the reciprocal of that. So raised to the power negative 1. Okay, so that's equal to how much? 6.626 times 10 to the negative 34. Oops. Okay. 6.626 times 10 to the negative 34 times 2.998 times 10 to the 8th, okay, times, what is 10 to the negative 2 raised to the negative 1? That's 10 to the positive 2, right? So that's 100, so times 100. That's that, and scientific notation, scientific notation is 1.99 times 10 to the negative 23. So that's about 2 times 10 to the negative 23. That's in joules. Okay? So that is the conversion factor for reciprocal centimeters and joules. So you say 1 reciprocal centimeter is equal to 1.99 times 10 to the negative 23rd joules. So you can use that as a unit of energy, even if you are not referring to a photon, okay? But that would be the energy of a photon if the particular photon is for light that has a wave number of 1 reciprocal centimeter. Okay. So typical wave number ranges, as you can see here, is very nice. Yes. Okay. You entered 10 to 10 squared in your calculator. Chances are you put 10 EE2. Mm-hmm. 10 EE2 is actually 10 times 10 to the 2, which is 10 to the third. Common mistake on your calculator. So enter 1 EE2. That way, and so you'll end up with just 20. All right, so typical wave number ranges, microwaves would be 1 to 100 reciprocal centimeters. So these are boundaries that are very easy to remember. Infrared would be 100 to about 12,500 reciprocal centimeters. If you remember your organic chemistry, when you did infrared spectroscopy in your organic chemistry, okay, the instrument that you use to take IR spectrum, okay, monitors absorptions in the 200 to 4,000 reciprocal centimeter range. Okay, you may have used the term frequency, okay, for wave numbers in organic chemistry, and it's understandable because frequency, what's frequency? C over lambda, right? And that is just C times nu tilde. So you can see that frequency is directly proportional to wave number. So frequency and wave number, the words tend to be interchangeably used because a higher wave number would mean a higher frequency. Okay? So the infrared spectrometer that you use in organic chemistry is called, is the range of frequencies you use there is said to be in the mid-infrared. It's right in the middle of this entire infrared range that goes from 100 to 12,500. Okay? Now, visible range, you're already familiar with that. You know that's somewhere between 400 and 800 nanometers. In fact, okay, this is just what? That is the 400 nanometers in wave. That corresponds to lambda of 400 nanometers, 25,000 reciprocal centimeters, and 12,500 reciprocal centimeters is 800 nanometers. Okay, so you can see your infrared starts off at around 800 nanometers and then goes longer wavelengths. Okay, so you can see those are very easy numbers to remember. And then beyond the violet, okay, we have ultraviolet, so 2,500 nanometers, 2,500 reciprocal centimeters. That's for 400 nanometers and beyond. 100 reciprocal centimeters, you should be able to easily show that that corresponds to a wavelength of about 100 nanometers. Okay, so those are really nice boundaries between the typical spectral ranges we deal with. Okay, so like I said, since frequency and wave number are directly proportional, then the terms frequency and wave number tend to be used interchangeably. Because when you say higher frequency, it means higher wave number. Okay. All right. Let's talk about photon momentum now. We said that light has a dual nature, right? We said that in some instances, the behavior of light is best described, is best interpreted in terms of a wave. And in some cases, its behavior is best interpreted in terms of it being made up of particles called photons. Now, the energy of each photon, we said, is going to be equal to h nu. And from relativity, the energy of any particle, according to relativity, the square of the energy is equal to p squared c squared plus m squared c to the fourth, where this p right here is the momentum, okay? Linear momentum. And in classical mechanics, Newtonian mechanics, based on Newton's laws, momentum is defined as just mass times speed. Okay, and that's what you learn in your introductory physics classes, right? Momentum is mass times speed. But if you apply relativity, momentum is mv over 1 minus v squared over. Let me rewrite this to make it easier to read. This is actually this is m naught. It's called the rest mass, the mass when the particle's not moving, okay? Times v over square root of 1 minus v squared over c squared. Okay, so this term right here in the denominator. That's the relativistic formula for linear momentum, okay? Now, since a photon is a massless particle, m naught for photon is 0, okay? Then it would seem that the momentum of photon should be 0, right? But since it is found to demonstrate momentum, okay, when it interacts with small particles, it is found to have momentum. Okay, the way you can justify having a momentum for a photon is when you apply relativity. Well, if you're approaching the speed of, when you're at the speed of light, what happens to your denominator here? When v is equal to c, what happens to this term right here? 1. And what is 1 minus 1? 0. So that becomes 0 over 0. So that sort of justifies giving a particle with a massless particle having a momentum, because 0 over 0 doesn't mean it's going to be equal to 0. Okay? So if you have a massless particle, then you'll say that this term will drop out, right? 0 mass. Then you can say that E squared equals P squared times C squared, so that is E equal to PC. What that suggests then is that the momentum of a massless particle has to be moving at the speed of light. So C is the speed of light. So the momentum of a massless particle is E over C. Okay? Or since a photon has an energy equal to h nu, that's going to be equal to h nu over c. So the momentum is h nu over c. Here's another way of looking at it. energy is Pc, it's also equal to h nu. So you solve for P. The momentum of your photon is h nu over c. But what is nu over c? Remember, lambda nu is equal to c. So what's nu divided by c? 1 over lambda. So that's just h over lambda. So what does this thing say? The momentum of a photon is inversely proportional to its wavelength. The longer the wavelength, the smaller the momentum. The shorter the wavelength, the higher the momentum. So which photon has greater momentum, an X-ray or an infrared photon? X-ray has more momentum. Why? Lambda for the X-ray is less than the lambda for an infrared photon. So your X-ray would have more momentum. Okay, so stationary hydrogen, here's an example here. And a stationary hydrogen atom releases a photon with wavelength of 122 nanometers. Calculate the recoil velocity of the atom. So imagine you have a hydrogen atom here. It produces a photon with 122 nanometers. So if the photon is released and it comes up to the left, what would happen to your atom? It's going to recoil in the opposite direction, law of conservation of momentum, right? So whatever the momentum of the photon is, that's going to be the increase in the momentum of your atom. And since your initial momentum of the atom is 0, it's a stationary atom to begin with, then whatever the change is, that would be the final momentum. So how are we going to do this? Yes. Okay, what's the momentum of the photon? H over lambda. Yes. Momentum of the photon is h over lambda. It's 6.626 times 10 to the negative 34 joules second. What's the wavelength of the photon? 122 times 10 to the negative 9 meters. And that gives us 6.626 times 10 to the negative 34 divided by 122 times 10 to the negative 9 equals 5.43 times 10 to the negative 27. 5.431. Okay. Three sig fix here. So 3 is the last digit there. That's sig fix. And what's the unit for momentum? Mass, unit of mass, which is kilogram, times unit of speed, which is meter per second, right? Is that what you get from joule seconds over meters? What's a joule? Kilogram meter squared per second squared, right? That's seconds divided by meters. So what does that give you? Just units of momentum. Meter squared over meters is just meters, right? And per second and second just gives you per second. So that's your unit for momentum. That would be the momentum of the hydrogen atom. So if the hydrogen atom releases 122 nanometers, it's going to recoil with that velocity, with that momentum. So what's the velocity of the photon, of the hydrogen atom? You can just say P equals mv. So what's the velocity of your photon? I mean your hydrogen atom. So it's going to be equal to P over m, which is 5.431 times 10 to the negative 27 kilogram meter per second divided by, what's the mass of a proton? Mass of a hydrogen atom. Mass of a hydrogen atom is 1.6 7 times 10 to the negative 27 kilograms. You remember how to figure that out if you haven't memorized that number? 1.008 grams per mole, right? And then you change it to, okay, 1 kilogram is 1,000 grams, right? And 1 mole is how many atoms? 6.02 times 10 to the 23rd atoms. Okay, so that gives you the mass for each atom. Think of it this way: 6.02 times 10 to the 23rd grams is equivalent 6.02 times 10 to the 23rd AMU, atomic mass units, is 1 gram. You can use that as a conversion. Okay. A mole of AMUs is 1 gram. Okay. So that is the correct number? Yes. Sure? Let's verify. Let me just verify. 1.008 divided by 1,000 divided by 6.02 times 10 to the 23rd. Yeah, 1.67 times 10 to the negative 27. Okay, so it's the mass of 1 hydrogen atom. So 1.67 times 10 to the negative 27 kilograms. So kilograms cancels out, and that gives you how much? 5.431 times 10 to the negative 27 divided by, oh, I didn't need the 10 to the negative 27, right? That will just cancel out, makes it easier. Okay, so 5.431 divided by 1.67, that gives you 3.25 meters per second. Okay. Now that's kind of a slow speed, so that's within the realm of classical mechanics. It's non-relativistic. Remember we said once you're approaching speed of light, you have to start applying relativistic formulas, but this one should be okay, 3.25 meters per second. Okay, so that's how fast the hydrogen atom will end up moving to the right if it releases that photon to the left. Okay, now there's some really nice lectures on YouTube about the development. Remember, what we did in this lecture is I just told you that this is the wave model, this is the photon model, right? Now, if you want to see how all those models came about, okay, these are very nice lectures on YouTube that you should really look at. This wave theory of light, the first 20 minutes of that lecture. Let's see if I can pull up that. I'm going to show you the whole thing. I need you to look at it, and I'll make my. This is a lecture from Yale. Okay, this is their typical Physics 2 lecture, which is lecture 19 of their Physics 2. So, it's a very good lecture. And then, the first 36 minutes of this lecture right here, and this is also from Yale. Okay, this is Introduction to Quantum Mechanics. Talks about the key experiments that led to the notion of wave-particle duality. Okay, and this last one is also pretty good. And this is a pen and pencil type, pen and paper type lecture. It's a very good lecture. This guy, Dr. Physics A, his channel has a lot. If you need to review a lot of your physics concepts, it's a very good channel to look at on YouTube. Okay, so oops, I'm looking at the wrong one. So that first 12 minutes should help you out with what we went over in this lecture. Now, in these lectures, if you move on to the last parts of these lectures, they go over wave-particle duality for particles, for electrons. We're going to go through that also in this class. So if you want to get a head start on the rest of the semester, just finish up these lectures, these video lectures. Okay. So I'm probably going to give you an essay assignment to post on Moodle pertaining to these, just to make you watch. Okay. All right. So this is this lecture.